I guess that if there is one brand which is worldwide recognized as, the Italian style and technology together, this is by far the Ferrari brand. Ferrari is probably the most well-known sport car and racing car and luxury car manufacturer in the world. And Ferrari has a long story. It's a long story. Ferrari, which started something around 1947, where the first Ferrari car was produced, and it was kind of spin-off of another Italian manufacturer, which was Alfa Romeo. And I have here just a few steps in the timeline of this company. So 1947, the very first car. 3 years later, 1950, the first racing car. A year later, the first Grand Prix won by Ferrari. And again, a year later, the first World Championship. So in 5 years, they went from the first car to the first World Championship, which gives you an idea of, the speed of innovation that was in the project. And that speed of innovation has never stopped for Ferrari, because I'm not going, of course, to tell you the entire story, but just to give you a couple of figures that you will hear even more during the presentation. Ferrari has a palmarès of 16 constructor titles and 15 drivers titles, which is quite nice record for a single car manufacturer. And of course, keeping competitive, gathering these numbers requires continuous innovation. And of course, speaking of cars, most of us will think, this has little to do with software. It's kind of, mechanical or material innovation. What's software? What's the role of software? Today we will learn that this is not the case. But just to provide you a very simple example, this is not a video game controller. This is an actual steering wheel of a Ferrari Formula One, which is not exactly what you would associate with a mechanical tool, and easy to guess that there is some software involved in building this kind of stuff, as we will learn later on in the keynote. And actually software is at the heart of modern racing cars, and not only because it is the core of controlling the car, but also because he has an important part in making decisions, and he has an important part in the engineering process. Again, just to give you an idea, when the very first time I went to Maranello to talk with our keynote speaker, I learned that during a typical racing weekend, they gather something like 25 gigabytes of data from the racing car, which is then used to make decisions, which means something like 20 terabytes of data, which is there ready to be mined in order to improve the car. And this is not the only area, because another area I learned is gaining more and more relevance is that of simulation in the cloud, because since a few years they have been forced to reduce the number of live tests, because there is a regulation that wants to save money and so enable the small teams to be competitive. And so most of the work they did in the past using the actual car, they do it now using simulation. And because need more and more power, most of the simulation is moving from machines to the cloud. So that's the context. So let me introduce Claudio Silenzi. Claudio Silenzi is the leader for hardware and software development within the Ferrari Formula One team. And he will tell about software engineering in Ferrari with a peculiarity. There is something that he likes to say every time, is, you know, the scale of innovation for us is 2 weeks. Because in 2 weeks from now, there will be another race, and the car will have to be there. And if you want to be competitive in 2 weeks from now, you have to be ready with the new release of the car, which means a new release of the software. Please join me in welcoming Claudio Silenzi. Possiamo far partire il video?
Thank you very much. I will try to to give you an overview of which is our activities in Ferrari Formula One. In Ferrari Formula One, we have a department of electronics. We do a lot of electronics, and I will show you very briefly. I cannot go in the details because a lot of information are very sensitive, so sensible. I cannot give you all the details. But it's important to say that Formula One is a motorsport where all the big players, car manufacturers in the world, Mercedes and other car manufacturers want to stay, because Formula One is one of the best platforms to test new technologies, new components, new materials, and of course, new software, new electronics, new tools, whatever. Ferrari, as a company, is a very old company, and is practically two companies in one. A first company that designed the Ferraris for road cars, Ferrari that if you have enough money you can buy if you want, so quite expensive. And a completely different company where I work, that is Ferrari Scuderia, or Motorsport for you, we call GES, that is Gestione Sportiva, that means motorsport in Italian language, where I work. Okay, the story, you have seen the video. In any case, I can tell you that Ferrari is in Formula One in every championship since 1950, without any interruption. We have been always there. We want to stay there. This is our core business, I would say, more than road cars. The story of electronics in Formula One is quite interesting because as electronics in a mechanical world, it is a story of fighting of electronics against mechanical world. So let's start from 1976. In those years, we had the first Apple computers, and in the Formula One car, there was practically no electronics because the ignition, the injection, and the instrumentation was mainly mechanical. In '85, we started having something electronics in the ignition and the injection of the car. And in 1999, we had the first experimentation of an electronic gearbox and clutch. I remember, I just seen, because I was not there, these devices was quite bulky, and also the electronics was quite bulky. And you have to take into account that one of our key points is to keep the weight very low. And so at the beginning, the electronics was very heavy, very big, and so it was similar to a mechanical device. So practically there was no gain having an electronic in the car. In '93, we start having the best for electronic in Formula One, the top, because practically the electronics was mature to be used in the cars, in Formula One car, because was smart, small, powerful, and so we had an era of traction control. That means a system that avoids the car spinning when you go on throttle. The drive-by-wire, that means that all the movement of the throttles and other parts of the car are driven by electric signals, and active suspensions. And this was the gold age for us. But in '94, FIA, the FIA is the governing body of Formula One, decided that there was too much electronics in the car, and the driver was too aided by electronics. So they decide to forbid any driver aids. That means the opposite of what happens for road car. No? Today, you have in road cars a lot of helps, system that watch your face to see if you are start sleeping, system that park your car, or maybe that now drive the car without the pilot, no? No, in Formula One, we want to go in the other direction. So practically, the driver needs to do everything. And so every aid to the driver is forbidden. Typically, the thing that FIA hate, that does want to see in the car, is the traction control. The traction control that avoid the car spinning is something that they say that is boring for the show, because any driver can just push the throttle and the car goes straight ahead without problem, without spinning, everything is very fine. I would say that I remember the races with the traction control on. I would say that the car was very similar one to the others. Now you can see car spinning, especially if it's raining. Other systems that are completely forbidden are the multi-downshift and the launch control. The multi-downshift was a system that Schumacher wanted at the beginning. I don't know if you know Schumacher was a pilot of Ferrari. I think it's famous for one that is following Formula One, and is a system that if you, from 7th gear, you ask for a down, it goes down with the gear to the right gear automatically, so to the 2nd gear, for example. The launch control is a system for the start. At the beginning, it was just a push button, and the system was controlling all the car in order to start in a quick way. Bidirectional telemetry, that was an idea from Ferrari. That was that today the car download a lot of data from the car to the box for the engineers. And we invented this idea that the data was going from the box to the car in order to help the driver to show to him some information on the steering wheel. This has been forbidden. Active suspension, ABS, is a system to facilitate the brakes. Brake balance, single ECU, other stuff like that. So, how we are organized? From this drawing, it's clear that Ferrari is a mechanical industry because we are just a small place there. We have a small place there. The Ferrari is divided in a chassis design, that is a department, and in power unit design, that is the other big department. These two big departments has in charge chassis for the chassis design, the aero simulation, and vehicle dynamics, that is a study of the car, how it behaves on the corners, on the curbs, on the straight lines. We are a part of the power unit department because electronics mainly help the power unit. We don't have a lot to do with chassis because all the 90% of control electronics in a Ferrari Formula One controls the power unit. The power unit, the name means that is not an engine, not an internal combustion engine. The power unit in Formula One is an hybrid unit. I don't know if you are aware of the rules of the Formula One, but this 1/3 of the power of a Formula One car comes from electric motors. We have 200 kilowatts of electric power coming in the power unit to push the car. So 1/3 of the total power of the car comes from recovery energy. So, those are our activity for the electronic controls for the power unit. We have a lot of software. I don't want to go so in the details, but we have internal combustion engine controls. Typical is torque control, ignition, lambda control, turbo control, fuel pump, and knock controls. I can tell you that a lot of this software give horsepower to the car. I mean, every day we study software, we do modeling, We work and we find 1 horsepower, 5 horsepower, 10 horsepower, and so on. From the beginning of this season, that started in November, up to now, we gained 20 or 30 horsepower just only with the software, without changing anything in the mechanical parts of the engine. Another part, very important, is the energy recovery system, that is the electric propulsion of the car. And this is a very brand new topic for us, and is new for everyone in the world, because if you have seen a hybrid car, you know that the hybrid car has a software inside that the purpose of this software is to use less energy, or to use at the best the energy, in order to have the lower consume of fuel. In case of Formula One, the topic is completely different, because we need to have the minimum consume of energy, but we need to win the race. We cannot go very, very taxing along the track. No? And so I stay at the minimum of the energy, okay, but you don't win the race. And so practically here we have a lot of maths, because we have an optimal control with 1,000 of parameters, and we have to minimize the energy consumption and the lap time, that are two completely different, because if you want to minimize the lap time, you need to use energy. And so when we faced people that was working on the software of hybrid system, they would say that this is not possible. Or you decrease lap time, or you decrease energy. On this topic, we have found a lot of horsepower, just only with the software, because we found ways to not use energy in one point and to give energy in another point. And this is quite tricky, quite interesting, I would say. For the chassis, we do very few things. We just control the gearbox. The gearbox is quite complicated device. We have a system of brake controls. It's not an ABS, but more or less is a brake control. We take care of the driver inputs, as we saw before. The driver inputs means to build a lot of stuff, electronic stuff, and to interact with the driver. Take into account that the driver is a very special person, and it requires every time new things, new buttons, new commands. It's like a child that wants to play a lot of stuff. So every race he wants new LED, something like that. And the launch control is a way of mapping all the car in order to allow the driver to control the car at its best during the start. The launch control is performance, because just only in the start we can gain one position in the race. What we have seen is a certain part of electronics, but electronics, the software and the electronics of the car also need to work for the electronics itself. I mean, we have a lot of work to do with the electronics of the car. For example, we need to supply the car. This is not easy, because we have a lot of voltages in the car, and so we have a lot of devices that supply all the devices of the car that are electrics. We have to build, design the hardware of the energy recovery system, that is an electronic hardware. We have the telemetry system. The telemetry system, I would say, it's a nightmare for us. It's very complicated to make it work. The driver interface, we said, the liquid pumps, all the pumps of the car. We have something like 20 pumps in the car. It seems stupid, but every pump has an electronics inside, a microprocessor inside, an operating system inside, and just a single pump gives you a lot of information. Get into panic says that there's problem, whatever. Just only with the pumps, we have people that is following what is doing this pump. We don't know. The knock detection system and data loggers. Knock detection system is a standard knock detection system that are in all the cars that you have. Data loggers is because we are not able to download all the data while the car is running, because there are FIA limitations on this respect. So the car logs data from all the issues in the car. And then when the car stops at the end of the race, we download all this data, and we should look at all those data. I would say that we are not able to look at all the data that we have. We designed the car harness in 3D. This is something that the car manufacturer typically don't do, because the Formula One car is very small, is very compact, the space, the room is very narrow, and so practically the wiring is treated as cooling tubes, cooling pipes, and so we have special car design that is able to just design in 3D all the wiring of the car. And then we have typical electronic stuff like ignition injection, sensors, hydraulic, and ground software application. I would say for sensors, we use the last findings in electronics, because we typically use sensors for high temperatures, we use sensors for high pressures that are not used in standard car. So when you look at the garage, at the box of Ferrari, typically people look at the car. But for us, if you can spot that there are computers there. No? There are computers because when the car arrives in the box, you can see that someone plugged an umbilical wire on the car, and so the car is in a local area network. And so we can see the car, for example, from Maranello, if the car is in Australia, and we use those laptops that you see here to tune the parameters of the car. The car has something like 30,000 tuning parameters. I don't know if you know what is the tuning parameters, but let me say that gains, offset, maps, whatever numbers that the software crunch and tune the car. We have 30,000. That 7% of these 30,000 typically are untouched, and but the 30% of these numbers are retuned every time by the engineers that look at the data and say, okay, I want to change these and these and these. So we do the tools to do this stuff, and every time we include in those tools protections and protections and protections. But our engineers are very smart. They succeed in writing every time the wrong value, every time. There's no way to avoid it. We place checks, cross-checks, whatever. They are able to enter always the wrong number, and every time we stop the car for a wrong number. The last time was a very stupid number of gain, and we stopped the car for one number. The tuning parameters, a wrong tuning parameters is like a bug. It's exactly the same behavior. Another tool that we need to provide to the engineers on the track is the software telemetry tool. After I have other slides on telemetry, I would say that this is the interface for our track engineers, for the engineers at home, that need to see the behavior of the signals. The FIA limits the number of channels to 1,000. This is a big problem because they are mainly mechanical engineers. They don't understand this stuff, but it's a problem. 1,000 channels typically are used from mechanical engineer to understand engine temperature, engine pressure, or whatever. They don't understand that our software guy needs to look at the variables of the code. No? So if you have just a routine that is running, I mean, for each software developer, they would need, I don't know, 100 variables just to look at, to understand if the routine is working well. And so for us, 1,000 is a very small number. It's very, very small. And so as Ferrari, we are working on a workaround that is going to cheat FIA. You don't have to say this is a secret. Just to have more channels for software guy. So there would be mechanical engineer that typically look at the car behavior, but then we have a lot of software engineers that are not interested if the engine is getting on fire. They practically don't care at all. But they're just looking at the variable, if the routine is running well, if the thread is running or the thread has been stopped by the real-time operating system, something like that. And I would say that every time to explain this to the mechanical engineer is quite difficult, but this is another staff that is in charge of electronics. We have a simulator. It's quite similar to a flight simulator. We're going to build another one. And this is a completely different task, as completely different software developers, different people that works on that, because here also the model of the car is a software that is very funny for us. So we have a virtual car, and we use real-time platform to run the model of the plant, of the car, the model of the power unit. No, the driver is real, because it's inside the car. And we need to move all this stuff in order to simulate the acceleration, like in an aircraft simulator. And this is very funny, because sometimes we find that just only writing the models of the car, we discover that the model is better than the real car, so we give suggestion to the vehicle engineers to change something in the car. And we use this simulator to improve our systems and to improve also our software, because we debug the software in the simulator. So when we have a new version, and we feel that this version of code is very risky, because, I don't know, it can stop the car, it can stop the engine, and so on, we test for the first time at the simulator. So we have young drivers that volunteers to go there with new software version that is quite dangerous. The same would apply for the test rig of the internal combustion engine. We have a lot of test rig for the engine. We have a lot of test rig for the energy recovery system, for the gearbox, for the brakes, for the hydraulic system, for any small devices. We have a lot of rigs. And in each rigs, we test new software version one day after one day, every day. We test new software version, because we can gain milliseconds in each device of the car. So, for example, in the gearbox, or also in a single pump. Another very, very funny electronic device that maybe you never notice is the pit stop light. I can show you very briefly, because this is a sort of industry secret, but it's not true. It's quite trivial. But every guy that you see with a circle has some device in his hand. No? This device is connected to an electronic system in the box and checks what each guy is doing. And so, for example, when there is a guy that is dismounting a tire and mount the tire, his device is saying to the system that the tire has been completely locked. No? So when all these people finish his work, so for example, mount the tire on the car, there is a semaphore there that gives the green light to the driver. So we are able to change the 4th tire of the car. So the car arrives, we change the tire, 4 tires, the car starts again in 2 seconds, more or less. The record is Ferrari 2 seconds and something. And this is allowed because there is an electronic system behind. I mean, there is a lot of young guys that are very athletes to be able to change. But in any case, in the old system, you would see in the old movies that the guy, when mount the car, say, "Oh, hey, I finished, no? So I finished with the hand, no?" And this was a lot of loss of time. The electronics is very quick because the driver just look at the green light. He does not look around, and when you see the green light, it starts, gives a lot of throttle. With a bug, we have almost killed the guy in front of the car because he was there with the green light, so yeah, it's a very funny bug. So the team is divided in 3 groups, our team of software engineers. We have application coders. Application coders typically use Simulink with autocode generation. I know this is not nice for software guys. Every time I tell that we use autocode generation, people say, "Oh, you, autocode generation, you're not a pure software guy." But these engineers need to provide controls of the car, high-level control of the cars, of the internal combustion engine, and so on. And so they typically talk with mechanical engineers, other engineers, and the language today is Simulink. This is spread in industry and educational world. And so it's more easy for them just to receive the model in Simulink and to code them. But this is not exactly so trivial. There is a long procedure because we don't have infinite capability in the car. But in any case, these people is able to understand Simulink code, Simulink blocks to be built in the car. We have another group that are embedded coders. Embedded coders are the more expertise people in our group because these are the real software guy, and they take in charge all the electronic system, the operating system that runs on the boards, the system that interconnects all the ECU in the car with several kind of different communication lines. And they work day by day because I would say that we have a lot of bugs. I don't know why. This is a typical software environment, and they work to understand what is going on in this board. And last, we have PC developers that do software for PC, and they know typically C, C++, C#, and they are expert in Windows and Linux system. So this is our rules. The race starts at 2 o'clock. And this has to be clear to the people that work in software engineering in our environment, because there is no delay to the countdown, like for the shuttle. No? The countdown has been stopped because there is a problem. No, the race starts at 2 o'clock. If you are there, good. Otherwise, you lose the race. There is no way to delay the start. So it means that we need to complete the software for a certain time. No delay, day and night. So for example, tomorrow we will have the first test at Monte Carlo, and if you have a bug, if you find a bug today, we have just this night, today and this night to fix it. There is no delay. And so we have practically a timer inside our company so that reminds us that there is a time for the commit of the software in hour. At this hour, you need to commit the software, to build and commit. There is time to go to validation, the benches. There is time to final validation. And there is time to give the software to the race engineers. No delay, it's not possible. For this reason, the software guy that works for us need to be very smart to give to me and to the company good compromises if we are not able to complete the software. We ask them, okay, we have this problem, what we have to do? We have 1 hour. And so they have to be smart, they have to find solution. They could say, okay, if we stop this thread, if you load this map, if you put this number here, maybe it works. And we have done races with what we say known bugs in the software that has been disabled somehow with a good compromise inside. So, this is a skill required for software guy if you want to work in Ferrari. Write bugs free, that is good. And we want that the people know the software perfectly because we have very, very few time. There's no time to learn how the software behaves, how the software works. So, new software guy simply work for us in 1 month to start understanding the code, but after they have to be very, very quick. It's a race also in the software. They have to be quick. They have to write code very fast. They have few days to do that. For this reason, we cannot do errors. Of course, it's funny, but it's like that. But we also ask to the software guy to admit to have done an error. This is not trivial. People usually try to don't say that there's a problem. We ask to the software guys, please, if you think that there is a problem in the code, please tell us before the race. And this is not trivial. They are not used to say that. They need to be able to work in team. I don't know, for any reason, software guys like to work alone during night in a place alone. No, they have to share the information. They need to understand mechanical engineers. This is a problem, I don't know, but the mechanical engineers have the right to life, I think. But okay, so the cons for them is that software guy need to stay there during the race, not in front of television, in front of telemetry. I need to answer the question that comes from the track. I would say that I see a lot of questions coming from the track engineer. Track engineers are, the people that attend the race in the track. No? So every time the car does something strange, there is no one other than the software guy to give an answer. What the car is doing there? What is happening? And so the software guy, the central part of Ferrari Formula 1 team, because they have to go in the code and to say, oh yeah, sorry, this is because you have put this number there. And this is very interesting because the technical director, that is the top of Ferrari Formula 1, talked with the last software guy to ask him, why there is a spike here? And the software guy explained, yes, because blah, blah, and so on and so on. And this is very funny because they talk completely different languages. And so. I will show you which is one of our main build, but we have a lot of issue in the car. So this is just an example of one main build. So we start from Stateflow Simulink MDL file, and we assemble the models with a descriptor. A descriptor is an XML file that simply places all the block in the real-time scheduling of the microprocessors. We have a lot of cores inside. And then, just at this level, we have 120 megabytes of MDL files for the control of the engine of the car. From this point, there is real-time workshop that compiles the file. We have 400 files in the car, C and H, .c and .h. 40 megabyte is the total amount of code of the main build. And also we build files for the tuning parameters right there. Then we compile, we create the binary file, and we create the calibration tools. The calibration tools are simply PC interfaces where a track engineer can write the numbers of the tuning parameters and download them into the car. This is the size of our business. It's quite small. We are not so many. So during one season starts in March. The season starts in March and in November. We do around 300 embedded code versions. We do around 100 PC tool versions. But we receive more than 1,000 of software requests. So this is the sport of Formula One is the best in requesting new software changes. We have a race inside on this stuff. I would say that in this big amount of software, we have done, in the last season, a couple of trivial bugs, very, very bad bugs. I don't know how to say what is a trivial bug, but we don't accept that someone write float instead of int. This is not acceptable. If this is the error, the software guy can do another job. And so we had a couple of them. We were trying to understand how this could happen, but this is not acceptable. We have tens of conceptual bugs. Conceptual bug means that we simply don't understood the specification. So we did something different from what the people would like to have. It's completely different, but this is normal. So this is the flow of our work. So there is a people that is called control engineers. These people are software guys as well. They simply are expert in control system. And so every day they simulate the code and the control system on PC with different tools. These control engineers typically provide specification to the software developers that transform these control systems in code. The software developers provide code, version code, to the testing engineers. We call them also application developers. And after that, the final production is made for track application engineers, so people that goes on track with the code. So this is my most used tool, is the calendar. Because the software in our environment is a race, as I said before. So this is June, and these are the races of June: Canada, Austria, and UK. And where you see the blue bars, the software is freeze. Why is freeze? Because, it's a mechanical word, so they don't want that you continue coding until just before the race. They say, okay, you have to stop 1 week before. So let me say that in Canada we will find a bug. We found a bug. So how long? This is what we have to do. We have Monday to do the analysis of the bug. The control engineer will try to give us a specification in half a day. We have a couple of days of coding. On Friday, these are fixed. We have an internal timer. On Friday, the testing will start. During the weekend, people will validate at the benches, at the rigs, at the simulator, the code, up to Monday. In Monday, we have to provide to FIA the code and the binaries. and we cannot do anything else. That's stop. So you can decide, or you go with a new version, if it's good enough, or you race with an old version. And so this is why it's a race, and why the software coder need to be very quick, because we have no time to wait, to retry, and so on. I would say that it's a very stressing job. I can tell you. I can tell you the software guy does not last a lot in our environment. So typically, they arrive that are very young after the academy world, like that. After 3 years, they will not shaved with a Coke. This is what happened is that a lot of engineers on track look at telemetry, and when there is something strange, they ask to us, what is going on, what the car is doing. I've heard that also what the hell is doing is the most used word in the Airbus. I said, I don't know, because also the pilot in the aircraft sometimes does not understand what the aircraft is doing. And the same happened to us. We have a lot of issue, a lot of software. Sometimes we see also strange behavior. We don't understand what is going on. And so there rise an issue, we call, on an internal tracking system. They simply write, oh, we see this on this lap with this driver, we see this glitch, we see this strange behavior. And they classify the request. They classify because we cannot cover all the requests. It's impossible. For example, during a race, we can receive something like 20 requests of modification, and we have 2 days to do that one, so it's not possible. So we asked to the track engineers to classify, and this, for example, for safety, reliability, performance, strategy bug, code bug, or because the driver wants it. So in theory, this would be the priority, in theory. So we should give priority to safety issues. In reality, we do what the drivers want, because I mean, maybe we have a system that can get on fire, and the driver wants a LED on because if I don't have the LED, I cannot race right. So we do the LED and not the system that gets on fire. At home, the control engineers see the horrible of all these requests, look at telemetry as well, trying to understand. They have 1 day to do this job. -5, yes, thank you. And they check the compliance with FIA regulation, because we have FIA regulation also for code, complete the specification, and give to the software developers the specification in detail. The software developers start coding the request, and then they give to the engineers, for the tester engineers, the result. And these are the rules that we are following in order to be so quick. So what I can say very quickly, and that is we don't do code refactoring during the races, during the season, because simply we don't have time. We typically don't do refactoring also at the end of the season, because you have seen that the refactoring every time change the behavior of the software. We don't know why, but we don't use static code analysis. We would like to do it, but in the main build, the static analyzer does not work, simply because the project is too big. We have 100 kilo simulating blocks of the main control, and so simply the system like polyspace get crazy, does not stop. One very quick mention for the governing body. Like any other event, we need to have umpires for the sport. The umpire, the referee of the sport, is FIA. The FIA write together with the team a technical and spotting regulation. This technical and spotting regulation involves also the code. And so every time we have a new version of code, we have to verify that the code complies with the technical regulation. Of course, we try not to comply, otherwise we don't win, but and it's a fight to understand if the software complies or not. How can do that? In the car, there is a small device that is called FIA surveillance data recorder that submit to the other ECU of the car a number that is called SID that refers to the certain sector of the memory of the microprocessor. And the microprocessor need to replay with the MD5. MD5 means CRC of this area. So if there is a suspect that Ferrari is cheating, I mean is doing in the software something that is forbidden, like some hidden traction control or some driver aids, what FIA do typically want to see the code, so we have to provide the code on track. So there is a software guy that is there just to explain the code. So they look at the code to see if comply with FIA regulation, compile the code there, and checks is the MD5 is the same number on the PC that they see on the car. If the two numbers are different, you are disqualified from the race. And this is a big stuff of job for us in this week, because we have to provide all this MD5. That's quite long. This is what we do in times of testing. So the software developers typically do the software, and they do the first debug of the code at the simulators. The testing engineer do the validation together with the control engineers. I mean, the people that write the specification do the validation with the testing engineers, so they can see if what they wrote in terms of specs complies with the behavior of the software. And then there is a final validation from the tracker engineers. We use HIL. I don't know if you are used to embedded systems. HIL is practically this small tower is like the model of a car. So practically in the testing procedure, we use this stuff. This is mainly used by software guy to simulate the code in the environment similar to the track, because they can just have like a lap race. You see here, for example, this is what they can simulate. This is like a car. I would say that Formula 1 is quite easy environment than the road car, because road car has to face with... Sono in ritardo?
No, hai un minuto per chiudere la slide.
Chiudo. The last one is that I would say that it's an easy environment because the maneuvers of the drivers are always the same, always the same. The driver, if you see these are 3 laps of a driver, are practically identical. It's different from a typical car manufacturer that has to imagine how an housewife drive the car when go to shopping or whatever with all the movement that can do. In this case, it's very easy because the driver simply repeats itself 60 times. And so for us, it's more easy to debug the software because we simply simulate a race, the following race. We have already recorded all this movement, all these actions, and we see testing this code, just repeating all the movement of the driver. These are tools that we use. We use whatever tools, whatever new tools we have, we can use. I would say that we have not a unique tools. We like that the software guy use the tool that he likes more. We know that every software guy like, no, I want to use Git because I'm used to that. No, I want to use Team Foundation Server because this is my house. And so we leave them using what they like. because we know we cannot force software guy to use something different for the editor, for whatever. So we have all the kind of tools we can use.
Yeah. Time for questions.
If you have any question.
We have time for a few questions. There are microphones over there. You can, yeah, just, if you can use the microphone, Carlo. Yeah, please go.
Carl Reed, La Trobe University. To what extent do you think the developers are holding the whole of the code in their heads so that they can identify the relationship between the bugs and the code, and also the extent to which are they people who've been doing this one project for a long time?
Vogliamo sapere cosa fanno. Yes, I don't know if I will catch your question, but you refer to what the software guy knows how the car behaves. Yes, in order to solve this question, each group of software is in charge of a certain part of the code, part of the project of the code. And they are able to understand very well how this code behaves. Is this a good question? Yeah, okay.
Carlo?
Yeah, you showed us, this very short, Carlo Ghezzi from Politecnico di Milano. You showed us this, very short time between requirements and implementation that you have to comply with. The requirements, I guess, they are natural language or, statements. And then you modify the code. I was wondering if there is a role, and what is exactly the role of anything that is in between those informal requirements and the code. You mentioned at some point that there were models. I just wanted to know more about what you do and how much you do at that level and how it helps.
There are strict rules. We have a lot of rules in order to follow this flow from the specification to the release of the code. And yes, the requests are quite different because maybe a request could be, look at that, I don't understand what is going on, something like that. Or maybe the request could be, I want a new map because with this new map I can gain some horsepower. No? And so the analysis could be quite different because in one case there is some like a bug, and so software guy need to understand the bug. Another case is a development of a new control system, and so it's a completely different analysis. In the second case, the control engineer try to understand the request in terms of development. It's a development. So the rule is not exactly the same depending on the request. Like that. For example, software guy receive a lot of requests to understand what is going on in the code or in the car, and they analyze that. So they bypass the control engineers. The control engineers typically try to understand the request in order to change the control systems, because track engineer can understand the control system, so they can ask for new development of the control system. So these are the two groups that take in charge the request, and then we provide a new version. There are a lot of meetings inside. We try to discuss and to take decision what is the best to do. And the decision is not easy. We can discuss, but I mean, we have few hours to take a decision. And then we provide to the rest of the company which are the decisions in terms of development for the next race. And this is a fight. It's a fight inside. Because, of course, people say, no, my request is most important for this and this and this, but at the end we have to take a compromise.
Yeah, we have time for another couple of quick questions over there.
Abhik Rajchodhuri from NUS. So my question is, how resistant are you to the change in the hardware because it may impact the software? And just related to that, what percentage of the code bugs, if you can share this data, were due to the Simulink model itself, and what percentage was due to the interaction of the auto-generated code with the underlying RTOS and the device drivers?
You want to know which is the percentage of the autocode?
No, just an idea. Like, are most of the code bugs coming because of the auto-generated code is interacting in funny ways with the underlying RTOS, or those errors are in the Simulink model itself?
If I were understood, I would say that the Simulink models are used just only for high-level control system. They interact with the real-time operating system, of course, directly.
Yes.
In terms of development, is 50% of the code, or less, made in autocode generation. The rest is made in C, C++, and C#. Is this the question?
No, the question was the errors, the bugs that
the bugs.
seeing, are they more in the models, or are they because of the interaction of the model with the RTOS?
The bugs in the autocode, I would say, I never seen a bug with autocode. I mean, if we are talking about how the code is generated starting from the Simulink model, I never see a bug. In this area, we have conceptual bug. I mean, we implement in the models of Simulink something that is not exactly what the requester would like to have. While in the C, C++, and C# code, we can have several bugs. I would say that most part of the bugs are in this directly coding software.
Okay, and how resistant are you to the change in the hardware?
We don't have change in the hardware during the season. Typically, the life of the hardware is 1 year, or more than 1 year, a couple of years. And so we did not show you the hardware side of my job. The hardware typically is freezed during the season.
Okay, we take just another question, and then two questions, but they have to be very quick. And
Karthik Pattabhiraman from the University of British Columbia. Quick question. So do you have any software fault tolerance or fail-safe mechanisms in the code so that if you observe a bug or an error in the field, the software can recover automatically, or is it all done posteriori after the race is done?
Yeah. I can tell you a couple of numbers. 2/3 of the code is not the main control, but is this fail-safe software. Yes.
And how do you test that? Do you do fault injection?
No, the diagnostics, the recoveries of the system typically comes from electronics guy. It's not an external request. I mean, typically we receive requests for having new features, and we have to take care of the recoveries and so on. This is typically an internal job.
Time for the final question, and then you will have a chance to talk to Claudio, because he will be around all day.
Bashar Nusseibeh from Leroy in Ireland and the Open University in the UK. I was wondering, in a male-dominated area like Formula One racing, how do you find it? Do you find it easy or difficult to recruit female software engineers?
It's difficult. It's very difficult. It seems strange, but I can tell you that we are seeking software guys now, and we don't find them. Sorry? Yeah. No, we have several sources for recruitment. The Formula One motorsport is made from, I can give you a small percentage, something like 50% Italian people. Then we have a big group, is like 20 or 30% from UK. We have from Germany, 10% from Germany, and the rest comes from several countries, more or less.
We have to stop now. Join me in thanking Claudio. And he will be around with us today. So if you have any more questions, just join in during the coffee break or lunch.
I would like to thank Claudio also with a small memory of his trip in Tuscany.
Grazie.
Thank you. Facciamo una foto insieme.